All right, so we're going to do an endothermic reaction with this one. So we'll toss up plots, something like this, and we've got products, we've got reactants, and we can put time down here, and we can have energy here, and then we've got there's my delta G, and in this case it's going to be positive since the final energy is going to be higher than the initial free energy. And then we've also got this energy of activation. So I have to add a little bit extra to get the reaction going. And this thing that I have circled, what do we call that? Transition state. So what is happening in that transition state?
Bonds are being broken and bonds are being made.
Yep. Atoms are transitioning from one compound into another compound, or one form to another form. This is the things that I have at the left side of the arrow and the things that I have at the right side of the arrow. They're being transitioning from one species to another. Okay. We want rate constant and rate law for this one. Okay, so I'm going to pick, I'll start off with trials 1 and 2. And I'm picking 1 and 2 because A, concentration changes, and B, concentration stays the same. So in doing so, B has no effect on rate. So when I'm looking at this, I have a 1.5 change. That is the factor. If I want to go from 2 to 3, I multiply it by 1.5. And if I want to go from 0.26 to 0.39, I also multiply it by 1.5. So when does 1.5 equal 1.5? When the exponent controlling 1.5 is a 1. Okay, so then we're going to, should we try trials 2 and 3? Why would that be a bad idea? Because they both change, so we wouldn't be able to isolate any effect of B. All right, so we're going to choose trials 1 and 3, and when I'm looking at 1 and 3, I get a threefold change here, and then I'm looking this rate. It's about 10. Are we okay with that? So up to this point, all the numbers that I've been giving you have been like dead on. It's like exactly 2 or exactly 4, exactly 8. That's not really lifelike. So when I'm looking at this one, the change is 10, and there isn't a solid a whole number exponent that I can use with 3 to get me to 10. So my options are, is this 3 to the second, or is this 3 to the third? Well, this is 9, and that's 27, and 9's a heck of a lot closer to 10 than 27 is. So if you had tried this same exact experiment instead of 3 times, but more like 300 times, what do you think would happen to that 10 value?
Probably get closer to 9.
Probably get a lot closer to that. You'll probably get some that look like 8, right? And then you'll end up averaging, everything will be averaged out. Okay, so this is going to be a second order with respect to B, bless you. And so I need to figure out what the K value is. So I'll solve, wow, that's not what I wanted to do. K is equal to rate divided by A to the first and B to the second. And so my K value, you could pick any trial you want. I'm just going to pick the first one because it's the first one. So 0.26 times 10 to the negative ninth, divided by 0.002 and 0.0075, and I'm going to square that. All right, so if I take 0.26, negative 9 divided by 0.002 divided by 0.0075 squared, I got 0.00231. So then the rate law for this will be rate is equal to 0.00231 A, B, B to the second. And that's it. So you should get the same value for the K, and if you don't, they'll be really close. So if we were really doing this, I would calculate each of the K values for each of the separate 3 trials and then take an average of them and report that.
Would
Right.
you be able to write that as 2.31 times 10 to the negative 3?
Absolutely.
Okay.
Okay, so let's do this one here. I've got, I got a doubling here, and I've got a doubling here. So it's first order with respect to x. I've got a doubling here. And what happens here?
I think it's 8 times 8 times.
35 divided by 4.3. Yeah, that's 8 times. Cool. So this is about 8. And so that makes this second order. No, that does not. That makes that third order. 2 to the third is 8. All right, so then I'll have, I'm going to pick the first trial again. So we'll have K is equal to 4.3 times 10 to the negative second divided by 0.0014 and 0.08 cubed. So 0.043 divided by 0.0014 divided by 0.08 cubed. 6 times 10 to the 5th. So its rate is equal to 6 times 10 to the 5th. X y to the third. Y to the third. And there's my rate law. So once I have the rate law, like, so who cares? What's it for? What's the purpose of getting one of these things?
Calculate the rate of a reaction.
So now I can put in any concentrations of X and Y I would like, and I'll immediately get a rate out of it. This could be super useful if I'm trying to do something with someone who's in a very bad situation. Poisoning kind of deal. Like, how much of this and this do I have to give them? There's going to be a point where if I give them too much, it's going to kill them, but they're not going to last very long, so I need to give them as much as I can without killing them, kind of stuff. So it could be a medical issue, could simply be an industrial process, but there's lots of applications. Once I have the rate law, I know the speed that I can get out of the reaction by putting in whatever concentrations I would like. All right, we're going to draw a cell with magnesium and zinc and calculate its voltage and determining redox. Okay. I'm sorry, what was it? And zinc? Okay. So there's some magnesium and there's some zinc, and it doesn't matter which one goes where. Inside of here, I'll put some magnesium, let's say nitrate, aqueous. And over here, I'll put some zinc nitrate, aqueous. I'll have myself a salt bridge, and I'll put in, say, potassium nitrate. I'll give myself a wire with a voltage meter in it, and I'll drop it in there.
Do you want us to draw that out?
That's what this question asks to do, yeah.
Oh,
Then I need to determine which direction the electrons are going to go. So where do you get that information from?
From the table in the notes.
So you have an activity series, and you just see who's on top, and I'm pretty sure it's magnesium.
It is.
So that means the magnesium is going to be sending electrons towards the zinc ions in the solution. So these magnesiums here are going to leave this bar and turn into magnesium ion going into solution. These zinc ions are going to go and attach themselves to this bar and we'll be adding magnesium to it. Oh, really? Come on. That's not cool. So then magnesiums are going to be sticking, sorry, zincs are going to be sticking to this bar. So this bar over here is going to be bigger, while the magnesium bar is going to be dissolving away. And the zincs that are ions that are in the solution are going to be disappearing. So what were the three ways that this thing could go dead?
The magnesium can run out.
The magnesium bar could completely dissolve away. What else?
Even though it's-
All the zinc that's dissolved in the solution gets all the electrons, and there's no more zinc ions in there. And then the last is any water dissolves or evaporates away. If there's not a connection, then it breaks. So that could happen with the salt bridge, or if this water level just evaporates down. Those are the other ways that it could go dead. Okay, so let's calculate a voltage. So let's look at the notes. Doo-doo-doo. 22, kinetic equivalent, blah, blah, blah. So it was magnesium and zinc. Did I just pass it? So the magnesium is written backwards up here, correct? So the magnesium is going to be generating a 2.38 voltage. Cool. Love that. And what about the zinc? Negative 0.76. Does it make sense it's negative 0.76?
Yes, it's gaining electrons.
Zinc would like to give its electrons away, but in this case, we're putting electrons on the zinc, so it's would prefer that not happen, so it takes power to give them back to it. Okay, and the nice thing about this reaction is magnesium's oxidation number is +2 and zinc's is +2, so it's 2 and 2, so they just cancel each other out. So they'll end up with a voltage, if I add these two numbers together, of 1.62 volts. Is that a good battery? Pretty good battery, right? Magnesium's not super expensive, zinc's not super expensive, and it's producing a 1.62 volts. So yeah, that's a pretty good battery. Okay, so let's talk about those terms: oxidation, reduction, oxidizing agent, reducing agent. So whose charge went down? No. The zinc, this guy over here was a zinc +2, and it turned into zinc with a 0 charge, right? So the zinc was reduced. Which means by default the magnesium was oxidized, but tell me why you know the magnesium was oxidized? Its charge went up, giving electrons away. Okay, so then we look at it from this other perspective. If I'm zinc, what am I doing to magnesium?
Taking its electrons,
So then what do we call that?
reducing.
What did I do to the magnesium? I oxidized it. If I'm zinc, I just oxidized magnesium. That makes me an oxidizing agent. What did magnesium do to the zinc? Magnesium caused zinc's charge to drop. So magnesium in this case is a reducing agent. That's really important in laundry. Not really important, but it's used in laundry. Bleach is an oxidizing agent. And when most things that are colorful because they've got excess electrons, and the bleach goes in and takes the electrons away from them, and the color is gone. The stuff is still there, which is why if you take a t-shirt, a white t-shirt that you've had for a long time that you really like, and it's still white, and you put it underneath the black light, it's like, oh yeah, there's the mustard I spilt on it, there's the ketchup, there's the steak. All that stuff is still there. It's bound to the cotton, but the bleach has removed the color from it. So that's well, when I worked at the Kells Pub in Corvallis and in Portland, they used black lights to check IDs, because stuff comes up under black lights, passports mostly. So you pass a passport under a black light and it has a different image. Has anybody seen the new Canadian ones? Freaking amazing. I mean, gorgeous. Whoever did the black light drawings, it's amazing. So I put it under black light, and I knew the things that you can't see under visible light show. So the guys that were bouncing, like my roommate was a bouncer, and he would just like laugh every once in a while. And I'm like, what? And he's like, this dude walked up with this white t-shirt on, and he looked like a leopard. Underneath the white t-shirt, underneath the black light, he looked like a leopard. That's how many black and brown spots were on his shirt. And you take the black light away, and it's just a white shirt. Okay, so when metals are transferring electrons to other metals, there's only one time when the transfer will actually happen. So in this case, this first one here, I've got magnesium metal and mercury ions. So the magnesium metal, this guy has his electrons, right? Because he's a metal. What about this mercury ion? Missing electrons. So if I've got one metal with and one metal without, I could get a transfer of electrons. And the transfer will occur if the metal that has them is higher on the list than the metal that doesn't have them. And that is the case with this particular instance. So the answer to this first one is yes. This is the only time that this can happen. So let's look at the next one. I've got zinc ions and copper ions. So the zinc is missing, right? And the copper is also missing. Does anybody have any electrons to give to anybody else? No, nothing's going to happen here. This is you trying to take a dead battery and charge another dead battery with it. They're both dead. They've both lost their electrons already. So how about this next one? This calcium has its electrons. This lead has its electrons. They're both metals. So does anybody need anything? Nope. So I've got a fully charged battery and another fully charged battery, and I'm sticking them together. What happens? Nothing. They're both fully charged. And then our last instance here, I've got silver that has its electrons, and I've got sodium that is missing its electrons. And this is an instance where something could happen, except in this case, the guy who's got his electrons is lower on the list. So this would be like trying to charge a fully charged battery using a dead battery. Neither the fully charged battery needs it, and the dead battery doesn't have anything to give anyway. So no and no. Are we good with that?